Is that okay?
Yes, yes.
Okay.
Okay, so we move to the next talk by Gaëtan Cane ou Cane?
Cane.
Cane. From the University of Nice, Sophia, Antipolis, who is going to talk about superdiffusion transition for a noisy harmonic chain subject to a magnetic field.
Okay. Thank you for the invitation. So I will start with a short reminder about FPUT chains. If you have some question, you can interrupt me. It's not a problem. So consider a system of n interacting particles. So each particle is labeled by x. And I assume that, to lighten the notation, each particle has mass equal to 1. So by Newton's law, we know that the derivative of the position, which is q here, is equal to the speed. And then, since the mass are equal to 1, the derivative of the speed is equal to the force which are acting on the particle. So here we are studying systems which have only local interaction, which means that particle x interacts only with particle x plus 1 and particle x minus 1. And here there are two kinds of interaction: linear interaction, which come from harmonic forces, and some nonlinear interaction, which are given by some function w. And alpha here is a positive number. Okay, and in this kind of system, the energy is equal to the kinetic energy plus the potential energy, and we can write it as the sum of the energy of particle x at time t. Okay, and the important fact in this kind of system is that the energy of the system is constant, which means that E of t is equal to E of 0. Okay, and then if we defined the energy current correlation, Sm, where here the bracket is the equilibrium measure of the system. This, when you increase the system size, if the conductivity of the system is finite, should converge to the solution of some diffusion equation, where kappa in this equation is the conductivity of the system. However, in this study this kind of system is really difficult due to the nonlinearity. And from numerical simulation, we believe that in this kind of system, in fact, the heat conductivity goes to infinity with the system size, and then the energy is not diffusive at a macroscopic scale. But due to the nonlinearity, it's difficult to study. And hence, one way to study this kind of system is to say, okay, I will put alpha equal to 0 in the equation of motion, and I will replace the nonlinearity by some stochastic noise. Okay, so here we consider the same system, but with an infinite number of particles, and here each particle lives in L2, which means that each particle has a position and a speed, which is a two-dimensional vector. And in the equation of motion, I here is just the coordinates of the vector. Okay, so since I erased the nonlinearity, the nonlinear interaction, the equation of motion are just linear. And what I can do is to add some small noise. So here epsilon is a small parameter. So we add some small noise. I will go back, I will explain what kind of noise. But the important thing on the important property that the noise has to respect is that it has to preserve some quantity on the system. As I told you, the energy of this kind of system is constant, but there are other quantity which are constant. For example, the momentum, which is in this context the sum of the speed. And the noise you put on the system, you want it to keep this property. So you want that the noise dynamics preserve the energy and the momentum of the system. So one way to do that is to let the deterministic dynamics evolve, and then at a random time, you said, okay, particle X and particle X plus 1, you exchange your speed. If you do that, the momentum will be the same, since it's the sum of the speed, and you just exchange two speed. And the energy will be the same, since the kinetic energy will not be changed. Okay, so this system was introduced by Basile, Bernardin, and Ola. And in this kind of system, they study first this system with a finite number of particles, and they proved that the conductivity of the system diverges when you increase the system size, which is the same behavior that I mentioned about the system with nonlinear interaction. Okay, and later, Basile, Ola, and Spohn study this system with an infinite number of particles, and using some two-step arguments, they were able to get the macroscopic behavior of the energy of the system. They proved that the energy of the system at macroscopic scale is solution of some fractional diffusion equation with exponent 3 divided by 4. I will explain how they did that, because I'm going to use what they did. And later, Saito, Sasada, and Suda study exactly the same system, but they add to the deterministic dynamics a magnetic field with constant intensity, which is transverse to the dynamics. And following the argument of Basile, Ola, Spohn, and Jarre and Komorowski, they were able to obtain a new fractional diffusion equation at macroscopic scale with exponent 5 divided by 6. Okay, so without magnetic field, the exponent is equal to 3 divided by 4, and with a magnetic field is equal to 5 divided by 6. And I'm going to explain how they did that and what happens if you put a magnetic field with a small intensity in order to get some interpolation process between the 3/4 and the 5 divided by 6 exponents. Okay, so let's do some introduction to explain the setting. So as I said, epsilon is the scaling and is the intensity of the noise, and is also the scaling parameter of your system. And the natural assumption is to say, okay, I will assume that at initial time, the energy of the system has some macroscopic profile density, which means that if I take J, a smooth function, and I study the limit when epsilon goes to 0 of the sum over all of the particles of the system of J times the mean of the energy of the particle X. Okay, I recall that E of 0x is the energy of particle X at time 0. This quantity will converge to some integral of GU WO, where WO is the macroscopic profile of energy of my system at initial time. Okay, so U in this talk is a macroscopic variable. Okay. Okay. And the question, a natural question is, okay, if I assume that initially I have a macroscopic profile or density for the energy, can we have a macroscopic equation for the energy density in some time scale? So the first thing Basile or Ola and Spohn did is to study this kind of question in T epsilon -1, okay? Because since they didn't know what macroscopic equation they will have, they used the two-step argument. First, they study the microscopic system and obtain a kinetic equation using a kinetics limit. So this explains the T epsilon -1 scale. And then from this kinetic equation, they obtain some macroscopic equation using another scaling limit. Okay. So, and in the first step, to go from the microscopic scale to mesoscopic scale, kinetic equation, they study some function, which is some distribution, which is a Wigner's distribution, which is a distribution defined on 0t to S times S prime. So it's a distribution. And S is the space of smooth function on R times t. We can think of S as the Schwartz space on R times t, where t, capital T, sorry, is a torus. So it's the interval 0, 1 with identified endpoints. Okay. And I will not give you the exact formula of the Wigner distribution, but I give you the information of why is this distribution important? Because if you take some smooth function j in the space S, but which does not depend on the torus, okay? So the variable of the torus is k. Then the action of the Wigner distribution on j is equal to epsilon times the sum over all of the particle of expectation with respect to the initial distribution, mu epsilon, of energy at time t epsilon minus 1 times the function j. So since we want to understand the behavior of the energy of our system, and we have this relation about the Wigner distribution, which this equation about the Wigner distribution is really as the same form as the equation for our initial assumption. Since we have this kind of result, we want to understand the behavior of the Wigner distribution when epsilon goes to 0. And this is exactly what Basile, Ola, and Spohn did, and later Saito, Sasada, and Suda. They were able to prove that the Wigner distribution, which is two-dimensional, recall, converges to some function f, which is a couple, where f is solution of some linear Boltzmann equation. So here, t is the time variable, u is the space variable, k is a variable in the torus, and I is the coordinates, so 1 or 2. So if we first forget about the right-hand side. Okay, we assume that the right-hand side of this equation is equal to 0. Then we have some transport equation, and this transport equation comes from the deterministic part of our system. So if you don't noise the system, then the Wigner distribution converges to this transport equation. And if you noise the system, this will give you some collisional operator, which is the right-hand side of this equation in purple. So this is a mesoscopic equation, a kinetic equation, okay? And just to mention the difference between the Boltzmann equation of Basile, Ola, and Spohn, and Saito, Sasada, and Suda, I recall the formula they obtain. So here, the collisional operator LB is defined is the generator of a jump process, as you can see. But inside there are some function theta, which depends on B, which are defined here. And if in the case of Basile, Ola, and Spohn, B was equal to 0 because there was not some magnetic field. So theta is constant, and VB, which is the speed of your transport equation, becomes singular with when B equal to 0. Here, if you see that when B equal to 0, VB becomes singular when K is near to 0. Okay, and because of this two behavior of the function theta and VB, this explains the different exponents we will obtain at macroscopic scale from the scaling limit we will do in this linear Boltzmann equation. Okay, so before studying this linear Boltzmann equation, we'll just make the link with random works. So just some reminder. So X is a Gaussian random variable if the probability that X belongs to some interval or set is equal to this quantity. And if we take some IID random variables, such that the probability that x0 equal 1 is equal to the probability that x0 equal -1 is equal to 1/2, like flipping a coin, for example, then if we define some function, some stochastic process but n as u plus 1 over capital N times the sum of the xn until n capital N squared, then this random variable belongs to L2 and in some sense will converge to the Brownian motion on R, which starts from U. Okay, and then we know that this Brownian motion has a Gaussian density for each time t. If you fix t, the Brownian motion has density FUT, where FUT is equal to this quantity. And then if you define rho tu as the expectation of some smooth function rho 0 taken at the Brownian motion, this is equal to the integral of rho 0 times the density. And this function will be the smooth solution of the heat equation with initial condition rho 0. Okay, so Brownian motion induces some diffusion. Here we are going to interpret our Boltzmann linear equation as a random walk, and we will not obtain a Brownian motion, but a Levy process, which explains the fractional heat equation that we will, fractional diffusion equation that we will have. Okay, so we can write our collisional operator as some function lambda times some sum of integral of some operator PB, which is a probability transition operator. Okay, and then we can define a jump process Ki, where K belongs to the torus and I belongs to 1, 2. Okay, it's the change of coordinates. So the process evolves as follows. It starts from Ki, and then it waits during a time lambda b, Ki, and when the exponential clock rings, the process goes from Ki to K prime j with probability Pb, and then it evolves again and again and again, and then we can interpret our linear Boltzmann equation as follows. You have a particle which starts from the position u with speed vb, and then the particle evolves according to a transport equation, and at a random time the speed of the particle changed, and then the particle will evolve again according to the transport equation, and then the speed will change, etc., etc., etc. And the position of the particle at time t is defined as zut equal to u plus the integral of the speed. Okay, 1 over 2 pi is because the speed is equal to v divided by 2 pi. And ks here is the continuous time process, which gives you the change of the different value of the speed. And then once we have all of this information, once we have defined k, I, and z, we have a semi-explicit formula for the solution of the Boltzmann linear equation using Feynman-Kac formula, which is FTUKI is equal to the expectation of some initial condition of our linear Boltzmann equation taken at some process zki. It's exactly the same idea that we have in the previous slide, where we had the heat equation, and we said that the solution of the heat equation can be seen at the expectation of some smooth function of the Brownian taken at the Brownian motion. Okay, so this is the same kind of argument. Okay, so here in the expectation with respect to ki, which this means that the process ki, capital K, capital I, starts from ki. Okay, and then we have that. Once we have that, we can write that. We can write our integral here, the integral of the position of the particle, which is the integral of the speed, as a sum, because as I said, the process K is a jump process, which means that it's constant, okay, during a random time, and then it changes value. So between two change of speed, the process is constant during a time that we have. Then, hence, we can change the integral as a sum of the time you wait between two change of speed times the speed. And once again, this is exactly, this is a form as a random walk we saw in the previous slide. So the one thing we have to do now is to find the good scaling in space and in time to obtain the behavior of ZUT. Okay. So now now we defined some alpha b, which is equal to 5 divided by 3. If you have a magnetic field on the deterministic system. Okay, I recall that B is the intensity of the magnetic field you put on the system. And if you don't have magnetic field on the microscopic system, then alpha B is equal to 3 divided by 2. Okay. And then what you can prove is that if you rescale your process by 1 over capital N, and you take at the time n to the power of alpha B, this will converge to some Levy process, where the Levy process is in fact an alpha B stable Levy process. Okay, so this means that if you define rho TU as the expectation of some function of YU, this will be solution of the fractional heat equation with exponent alpha B divided by 2. Okay, so the Levy process induce some fractional diffusion equation. Okay, and then we have our answer because, okay, I recall the formula for alpha B. Now I know that my random walk converges to some Levy process, okay, which generates a fractional heat equation with exponent alpha B divided by 2. So what I can do is to say, okay, I defined the solution of I defined rho B as the solution of this fractional heat equation. And then what Jara Komorowski, and Ola proved in the case of when you don't have any magnetic field, and later Saito, Sasada, and Suda when there is a magnetic field on the microscopic system, is that if you rescale the function f, which is the solution of your linear Boltzmann equation, as n alpha bt and nu, then this quantity will converge to rho b, which is the solution of the fractional diffusion equation. Okay, and the different exponents you obtain is due to the tails of the random walk you have, because of the lambda, because of the theta b and the VB I mentioned before. Okay, so before I present my results, just make a conclusion about what we did here. The question was, okay, I assume that at initial time, I have some density for the energy of the system, okay? And the question was, can we have an equation for the density at each time? Can I have an equation satisfied by this density? So the answer is yes, and the solution is, the equation is the fractional diffusion equation with exponent alpha b, but here I made a two-step argument. Okay, first they proved that the microscopic dynamics using the Wigner distribution converge to some linear Boltzmann equation, and then from the Boltzmann linear equation they obtained some fractional diffusion equation. So this is a two-step argument. The one-step arguments, so from Wigner distribution to fractional diffusion equation in one step, is just done for the case B equals 0, so with no magnetic field. But now, in 1 minute, I want to explain what I did. Here we have two different exponents.
Yes,
3 divided by...
Yes? You have 2 minutes left.
Sorry?
You have 2 minutes left.
Okay, thanks. Okay, so first you have one exponent 3 divided by 4 when you don't have any magnetic field. And when you have a magnetic field, you have 5 divided by 6 for the exponent of the fractional diffusion equation. So a natural question is to say, okay, I will replace B by Bn, which is equal to B times n to the power of minus delta, where delta is positive. Formally, if delta equals 0, the magnetic field is constant, and I should recover the fractional diffusion equation with exponent 5 divided by 6. And if delta equals infinity, I should recover the fractional diffusion equation with exponent 3 divided by 4. And in fact, so here now, from the microscopic scale to mesoscopic scale, there is no transition. Okay, you can prove that at scale epsilon minus 1, you don't see anything. So we study the transition for the Boltzmann linear equation. So here, everything depends on n. Okay, and here we defined alpha delta, which will replace the alpha b we had before, by 5 minus delta divided by 3, if delta is less than 1/2. Observe that if delta equals 0, then alpha theta equals 5 divided by 3, which was the exponent we had before when the magnetic field was constant. And when alpha delta, and when delta is larger or equal to 1/2, alpha delta equals 3 divided by 2. Okay, and then what you can prove is that the rescaled linear solution of the linear Boltzmann equation converges to rho delta, where rho delta is solution of some partial differential equation. I didn't give the partial differential equation, but I give a graph to explain the transition. So on the vertical axis, you have the scaling in time. On the horizontal axis, you have the value of delta. When delta is between 0 and 1/2, the partial differential equation is the fractional diffusion equation with exponent 5 divided by 6. For delta larger than 3 divided by 2 is fractional diffusion equation with exponent 3 divided by 4. And at the middle, you have some new operator. And when you send B to 0 or infinity, you recover the true fractional diffusion equation you add. Okay. Thanks for your attention.
Thank you very much. So are there some questions in the room?
Thank you very much for a very nice talk. I really didn't understand your last point. So this intermediate operator, so it is really this d delta, it is really not Laplacian in some power, or it is?
Yes, yes, exactly. When for delta equals 1 divided by 2, dB is not a fractional operator.
So you do not know what it is really? Yeah.
Yes, yeah, no. I have the formula of dB, which allows me to obtain the limit when b goes to infinity and b goes to 0 to get the fractional operator.
So how it looks like then this d delta in this intermediate?
It's just a non-linear operator.
Yeah, okay.
Don't remember exactly the formula, sorry.
Yeah, okay, no problem. Thank you.
Any question online? So if not, we can thank Gaëtan again. Thank you.
Thank you.
And we switch to the third talk.
Yes. Hello, everybody.
Hi.
Hi. So I don't know if I can share the screen. Maybe yes.